quickly as we go through this because there's an awful lot of information I want to stuff in through here during the brief period of time that we have together. So it's somewhat intentional, but I think you'll enjoy the information you're about to share. Now, Peter Drucker says that quality in the service or product is not what you put into it, it's what the customer gets out of it. So what we want to ask is, you are the customer of capability indices, not your customer, but you are. They're supposed to be telling you something about your process. However, what is the point of capability indices? Why do we even bother with this exercise? Who cares? And most importantly, what are you getting out of capability indices? Do they completely satisfy your needs on what you need to know about your process? Now, this presentation is going to be a little bit different because most presentations provide clarification or a better way to accomplish a task. This presentation shows the risk that calculating capability indices might be a non-value added effort. In 1991, the Automotive Action Industry Group, or AIAG, was formed and consisted of the big three. One of their objectives, believe it or not, was to standardize the reporting requirements from suppliers and in general of their industry. I want you to note as we go through this presentation that there's a lot of references. So most of this stuff I'm not making up. I've gleaned a lot of information from a variety of sources. So when you get your PDF, you'll be able to verify some of this information based on the references on these slides. A standard reporting technique that they required was capability indices that represented the ability of a process to make parts to specification. It seemed simple at the time. Calculate a ratio of the output of the variation to the permitted tolerance. And as Dr. Phil would say, well, how's that working for you? So I want to take a moment to step back and check out the basics of concepts of the process capability before going into some of the pitfalls. First of all, let's review some of the rules of life. First of all, the correct answer to any question is, it depends. Secondly, just because you can calculate it doesn't mean that it has meaning. So for example, we have an orange and an apple. So 1 times 1 equals 1, right? Well, you can calculate that, but as you can see, that has no meaning. So again, just because you can calculate it doesn't mean it has meaning. Number 3, customers are not always right. Some of them aren't trained to the information that they need to know to make correct information, so you may have to train them. For example, customers are looking for a quick and easy way to determine if their suppliers are satisfying their needs. They rubber stamp capability index requirements on dimensions when really it's about the process. Not all indices and their acceptance criteria will work with all processes. So just because you can rubber stamp it doesn't mean that it's actually applicable. Many customers demand calculation of capability indices with very little knowledge of the validity for your process or the meaning of the resulting value. Some customers assume if a capability value is above some value, the process will not make bad parts. That is absolutely incorrect by definition. Suppliers are looking for a quick and easy way to satisfy their customers. They've been demanded to calculate this data, so they go out and do it. It's a quick and easy, but quick and easy doesn't work. Understanding process variation and its controls would be far more productive. And number 4, stable processes are only supposed to be normal if the process is a normal process to begin with, and not all of them are. Not all processes have normal outputs. For non-normal processes to have a normal output does not mean that it's stable. In fact, it proves that it's not stable. So the assumption that if you're getting a normal output, that it's stable is not always true. Often non-normal processes are masked by gauge and measurement error, both of which tend to have normal distributions. So just because you see normal doesn't necessarily mean that that's what your process is doing. It may have been masked by errors in gauge and measurement. And a test for normality does not prove stability. By the way, a normality test that you may be familiar with does not tell you that you have a normal distribution. It only tells you when the data makes it unlikely that you do not. And that's a key difference. Any frequentist test is constructed to disprove something. So for example, a dry sidewalk is evidence that it didn't rain. A wet sidewalk might be caused by rain or a sprinkler system or something else. So a wet sidewalk can't prove that it rained, while a not wet one is evidence that it did not rain. Every evaluation of a process capability has to have a process and a goal. To evaluate process capability, the process and the goal must be accurately defined. So let's take a look at some definitions as we get deeper and deeper into the process. So for example, you might have a process called running. Well, with running, a man is capable and a baby is not capable. Is that all you need to know? Well, the correct answer is that depends. So a similar decision for capability might be cutting an OD. A lathe is capable, but a drill is not capable of doing that. So what if we look into running uphill? A man is capable of running uphill. So as a similar decision to cutting a precision outer diameter, a lathe is capable of cutting a precision diameter, but a bench grinder is not capable. Now you might have to run uphill to a hospital to deliver blood with blood in good condition. Now we have good condition, which becomes a product tolerance. That's a similar decision to cutting a precision outer diameter to an extremely tight tolerance and a smooth finish. A grinder is capable, a lathe is not capable. Capability indices that measure how well a process can maintain output within that tolerance are CP and PP. Now, running uphill to get to the hospital to deliver blood with the blood in the best condition. If you go too slow, the blood might get warm. If you go too fast, it gets shaken up and may break down. So now we have a more critical tolerance, not just that you have to go uphill, but you have to go uphill in an optimum time. The scenario is an example of how the Taguchi loss function is used to drive people to center their process. That means that there's a certain point where there's an optimum speed, for example, and if you go too fast or too slow, then it's going to degrade its function. With that thinking, the example at the top will have a larger negative impact on the customer than the product on the bottom, because it's more towards the area of defective product, whereas even though you have a wider spread on the bottom example, it has more in the good zone or the sweet spot. Yet since the top distribution is so small, the CPK is the same as the probability of going beyond the specification for those two are the same. So really, if you look at the Taguchi example versus the CPK, CPK does not necessarily mean that you are centered. However, being centered is where you want to be for this particular example. Even though the index will make you think that they are equally as centered, they are actually only equally as probable of falling out of specification. CPK is not really a measure of being centered, although many think it is. A similar decision to cutting a precision outer diameter close to an optimum target value, you can do that much easier with a CNC control grinder, especially if it has automatic tool control, where it's much more difficult with a manual control grinder. But on top of that, is being centered always an economic advantage for the customer and worth the effort? Well, the fact is, if the loss function does not increase dramatically as it approaches the specifications, as you see on the right-hand side of the example, it becomes less economically beneficial to drive the process output towards the center of the tolerance. Forcing yourself to constantly adjust to a central target is not economically necessary means that the operator intervention becomes the process. That means more and more operator intervention to get it centered. Their adjustments actually become the process instead of toolware or whatever the process is itself. Not only that, it's over control. And over control is something that goes all the way back to QS 9000 of something you want to avoid, not encourage. Now, the process running uphill to get to a hospital to deliver blood with the blood in the best condition over a long period of time. One of the interesting things about most capability studies are they're very short term. Oh, you can prove that you can do it over, let's say, 300 pieces. But what about the next 300 pieces? Or what happens if you have other periods of time? What if you have to do it twice in one day, for example, in this example? Maybe he can run up to the hospital once, but what about 2, 3, 4 times? Do you think it's equally as effective each time? Well, you don't get that from the typical capability studies. So this capability indicates the ability to meet the requirements over a period of time under various conditions, which most capability studies don't do. Capability indices that measure how well a process can maintain output close to a target value. And a target value over a long period of time are your OEE, overall equipment effectiveness, and your first time yield. So let's take a quick look at the math. Process capability is the ratio of the tolerance permitted to the variation a process exhibits. The key is having the correct distribution model of the process variation to compare to the tolerance. The wrong distribution, as in assuming normal when the process is not, gives incorrect conclusions. The correct distribution is best determined by curve fitting. Now, there's two popular capability calculations. You have process capability and process performance, and that's how these are identified in the SPC book for AIAG. CPK is commonly used for commonly used capability, but you'll notice it has only common cause variation. So by definition, it does not include special causes, where process performance has both common and special cause variation. A lot of people don't realize that. And where does this 6 sigma come from anyway? Well, it comes from the process model assuming to be a normal distribution. And when you assume that, you look at where does the normal distribution end? Well, it ends at plus or minus infinity. And plus or minus infinity makes for some very hard math. So what they do is they decide arbitrarily to have it stop at plus or minus 3 sigma, about the mean, or 6 sigma. No more magic other than that. So process capability, CP or CPK, the variation of the process arises only from the common causes. So based on this, if you have a CP or CPK that's considered capable, can you still make bad parts? I've often heard from customers that, well, your capability was good. How can you make bad parts? Well, by definition, you can, because it does not include special causes. And when special causes occur, you have the possibility of making bad parts. Capability and process capability only considers common causes. So here's an interesting point, especially for those of you in automotive. What if you were to actually perform a capability study based on the AIAG requirements? What would you have to do? Well, what's interesting is there's nowhere in the AIAG books that it shows you step by step how to do a capability study. In fact, if you look at the right-hand side of this slide, these are all the different areas you have to go to develop a process for a capability study to AIAG. It includes the 300-piece consecutive part minimum run on one process stream, or longer-term historical data from similar processes if permitted by the customer. You're supposed to take 25 subgroups of at least 100 readings, at least 4 readings per subgroup, and chart them. A lot of people don't realize this. You're supposed to either use an X bar and R chart or an individual's moving range chart if permitted by the customer. Then you calculate your CPK. In order to do that, it must be stable, which means your process is in control. Well, how do you know that your process is in control? Well, that means you would have had to chart it anyway. You move the out of control data as they represent special causes for CPK, and then only calculate based on the common causes. For PPK, known and predictable special causes and output meeting the specification are used. If you use less than 100 individual samples or an unknown source of variation, then you have to contact your authorized customer representative, which is an AIAG way of saying, we don't know what to do. Because trust me, if they don't tell you what to do in the books, the authorized customer representative probably doesn't have much information either. Now, I've also supplied from the Quality Digest an interesting process flow for capability study. It's in the PDF, so you may want to take a look at that too, but we're not going to go through this step by step. Now, what are you supposed to do when you don't meet those requirements in automotive? You're supposed to contact the customer if acceptance criteria cannot be attained by PPAP submission date, supply corrective action plan, and a modified control plan, typically providing 100% inspection. The 100% inspection methods are subject to review and concurrence by the customer, by the way. Variation reduction for efforts shall be continued until the acceptance criteria is met or the customer approval is received. So let's take a look at the limitations of process capability indices. Capability indices are a function of process average and standard deviation. These are summary statistics. They're not very useful if the process is non-homogeneous, and most processes are non-homogeneous. Non-homogeneous processes tend to yield multimodal distributions. So how do we know that? We take a look at the total variance equation, which is the sum of all the variances that are affecting the process. If there's only one variance affecting the process, then you could have a single mode. However, once you start having additional variations, then you can have multimodal outputs because they all participate, and each one of these can have their own distributions, by the way. The traditional SPC charts are great detectors of non-homogeneity. But if you already have that, you don't really need to detect it. And not all non-homogeneous processes are unstable or incapable. So just because you detected non-homogeneity does not mean it's unstable, because it may be a stable process even though it's non-homogeneous. We also publish this number as if it's exact. Oh, the process has a 133 or a 167. If one were to calculate the confidence intervals around the estimate, we would see exactly how inexact that estimate actually is. Focusing on a single number diverts us from the incredible insight available from even a simple run chart of the data. So there's no way that you can determine really what that process is going to do over time just by a simple 3 digits and a decimal point. Probably the only person that would put that much value into the power of one number would be a lottery winner. And since we're all here, we're probably not lottery winners. It's typically used to describe a process after a very short run. The sample size is too small to be predictable. So CPK, PPK, capability indices are not very good predictors. Often subsample of short runs such as 300-piece PPAP lot, it can be too inadequate to describe all of the output distributions. Sample represents too little of the long-term variation the process will see, such as material lots, operators, machine conditions, environmental conditions. It's almost impossible to determine how they're going to affect the process with a typical short-term capability study. So once again, one number does not have enough depth to describe a process over its entire life. The resulting value may not be very repeatable over time and therefore has very limited power as far as a prediction tool. Yet people tend to use it as a prediction tool. Oh, you said you had a 133, you should still have a 133. Is it, well, based on what? That was a different lot of steel, or so on and so forth. Unfortunately, many people believe it is a powerful prediction tool. It simply is not. It can be more adequately described as a macro or 20,000 foot tool, but that's about it. So let's look at some of the problems with capability indices. From the AIAG SPC book itself, it says that the capability indices are not the plug and chug tool people they have been led to believe. To quote it, automotive companies have set requirements for process capability. It is the reader's responsibility to communicate with their customer and determine which indices to use. So they're saying the book can't even tell you the right one. You need to figure it out on your own and work it out with your customer. In some cases, it may be best to use no index at all. Who's read that part of the book? It may be best to use no index at all. It's important to remember that most capability indices include the product specification in the formula. And this is key. If the specification is inappropriate, like how did you develop the specification to begin with, or not based on the customer requirements, much time is wasted on trying to force the process to conform. In the AAG book, it also talks about misunderstanding and controversy. This manual recognizes both misunderstanding and controversy surrounding the fundamental concepts and definitions regarding process control, capability, and performance. Now, this is fascinating. It's not the purpose of this manual to fully resolve these issues. Well, then where do you go to fully resolve these issues? But to expose and discuss them in an extent that allows each reader an opportunity to develop a better understanding of them in order to provide value and knowledge for a continuous process improvement. I'm not sure how you can get better knowledge if they left you hanging within misunderstanding and controversy. You cannot run this specification on a shop floor if you're required to meet the capability greater than 1.0. A lot of people will go out, start up their process, and try to run the process to the tolerance. It's impossible statistically for that to be capable. You have to automatically reduce your working tolerance to 75% if you want a 133 minimum of the customer tolerance in terms of a CP and more in terms of CPK. The further the mean is away from your target, the less tolerance you have available to meet your capability. One of the things that people don't realize is when you commit to CPK or PPK, you've cut back on the tolerance that you're allowed to use on the shop floor, and a lot of the process people, A, don't understand it, and B, can't believe that somebody would do that to them. But it's true. The acceptance criteria for indices does not apply to all process distributions. If you look in the AIAG book, it states specifically processes with one-side specifications or non-normal distributions. The CPK and PPK acceptance criteria assume normality and a two-sided specification with a target in the center. When this is not true, using this analysis may result in unreliable information. So when a customer makes you do a 133 on roundness, run out, things that are unilateral, it's telling you right there that this is an inappropriate analysis. Capability indices are complex transformations of the original data. Since they are ratios, they behave in a complex manner. This means the process may behave one way while computed capability indices behave another way. In short, there's no particular relationship between the predictability of the process and the predictability of the capability indices, and that comes from Dr. Wheeler. Performance indexes are descriptive measures of the past and do not provide any useful information beyond an estimate of fraction nonconforming. In Montgomery's book, he states that Kautz and Lovelace back in 1998 strongly recommend against the use of PP and PPK, indicating these indices are actually a step backward in quantifying process capability. They refer to the mandated use of PP and PPK through quality standards or industry guidelines as undiluted statistical terrorism. That is, the use or misuse of statistical methods along with threats and or intimidation to achieve a business objective. That's some strong wording. Peisdeck states that as with most things, process control analysis is a worthwhile endeavor, but one with pitfalls. I advise that you use techniques of process capability analysis, including process capability indices, however. First and foremost, get the process into statistical control. Be sure the curve fits the data, especially in the distribution tails. Never lose your skeptic's eye. Use common sense at all times. Verify the predicted performance actually occurs with the future runs. This is much more likely to be the case if the process is kept in statistical control. Don't use process performance indexes. Instead, use control charts to help identify special causes, remove the special causes, and compute the process capability indices of CP and CPK. Now, what would be my preferred approach for process capability analysis? Well, let's take a look at the steps we have with AIAG, which is the 300 consecutive run, and then preparing a chart. After that, I would just stop, because beyond that step, you lose, not gain, information. Why bother investing the additional effort? If you have a chart of what happened during that period of time, you have more evidence of what that process is capable of doing than any single number that you would ever provide anybody. In fact, more often than not, when my customer asks me to show them capability, I slide a chart across the table. Much more meaningful than those magic digits. Even as a macro or 20,000 foot tool, it still needs to be evaluated correctly to have any value whatsoever. Often that's not the case. People look for a fast and dirty tool to rubber stamp on their processes to satisfy their customer. So later on, we made some fantastic time, but later on we're going to talk about calculating capability for non-normal precision machining processes, which does not use CP, CPK, PP, or PPK, and also how to calculate unilateral tolerance capability, such as concentricity, roundness, and parallelism. So we got done quicker than we thought, Norval.
Yeah, that's great. Anyway, looks like we've gotten to the end of what you planned on talking about today. Like you said, we made great time. Just to kind of let everybody know, Bob and us have been kind of back and forth here over the last 24 hours. He has some case studies that he wants to share, but in the interest of time, we're going to schedule a part 2 session for this particular talk. It'll be on Tuesday, November the 7th at 12 noon Eastern time, so be ready for that. That'll be like a bonus, I guess, for today. So for those of you who come online on Tuesday, November the 7th, it'll be an extra 1/10 of an RU, so the certificate will say 0.2 RUs rather than 0.1, since it will be for 2 hours. So what we're going to do is we're going to open the floor up for questions. If you have questions for Bob, we'd like to ask you to type them into the chat box, and Bob will be happy to answer them for you.
There was one question whether homogeneity is equal to the normal distribution. There's a high probability that if all you have is one distribution, one variance working with a product or working on a process, that it's going to be normal. However, if there's any physical limitations to that process, brick walls, if you will, that you can't go beyond, then you're going to end up with a non-normal distribution. Think in terms of roundness. If you have roundness, as you approach perfect roundness, you can't go into the negative area. So it stops there physically, and that's not going to be a normal distribution. The true position. Well, that would probably take a whole nother presentation. I and the people who deal with this on a day-to-day basis fight with this an awful lot. Especially when you have, whether you have MMC or whether you have, regardless of feature size, it's a challenge anyway you slice true position. Usually with true position and MMC, I'm looking at somebody trying to define something that works best with a go, no-go gauge. And what I do in that point in time is I present the data as a go, no-go attribute capability study. And the attribute capability study is pretty straightforward. You do 125 parts and they better all meet it. If they don't, then you're really not capable. But when you have people that are trying to calculate variable information within true position, and there's been a lot of people that have attempted to do that, it gets dicey to the point I'm not so sure even the customer would know what you're providing them after you put all that effort into it. Aren't predictions using SPC what Dr. Deming referred to as an analytic study for which statistics can't be used? Well, once again, SPC, Shewhart charts really are not predictors, they're monitors. What they are looking for specifically is whether or not you have a special cause. That is the whole point of the exercise. However, as long as you are running your process within those capabilities and you don't have your special causes, at least at that point in time, you know what the process is behaving as it's expected, and you have a little better idea of what it's going to do as long as you maintain those controls. But yeah, I wouldn't say that SPC is a predictor, but it is a better evaluation of what has happened during the study than any calculation based on capability. Am I an advocate of short-run SPC? Well, as we stated early on, the answer to that of any question is that depends. I am not an advocate of short-run SPC for machining, and I'll tell you why. Most short runs in SPC, the machine hasn't even had a chance to warm up and achieve a steady state. One of the special causes is startup and warm up. So you don't need SPC to tell you that you have that special cause. You know you have a special cause because that's exactly what's occurring. However, I normally will run SPC just to make sure that I have information for making adjustments during that period of time. And because it's a special cause, oftentimes I will check it more frequently until it reaches steady state. We shift the process towards the UCL for tool wear reasons and PPK was way too low. If you're dealing with tool wear, and we'll talk about this at the next presentation, I highly recommend that you tune into that one. PPK, CPK are not appropriate for tool wear, period. It's a non-normal distribution and it's not appropriate whatsoever. So we will go into more details in that next presentation. I highly recommend that you tune in for that. If you don't use indices for predictors, what do you recommend? I'm not so sure that there are any mechanisms for predictors except for long-term data collection, because again, there's no way that you can determine on the short term what's going to happen long term as far as material changes, temperature changes, all those things that can happen over time. Only long-term data can predict that. What is your thoughts on confidence and reliability tolerance intervals as an alternative to the process index? Well, you know, that's interesting because really, first thing you have to know is the tolerance provided by the customer real? You know, has it actually been defined based on its performance, or was it just determined because, you know, it seemed to be a good idea? Because oftentimes if it's determined because it's a good idea, you might have it way too tight, and now you're going to try to calculate based on something that's not real. However, there may be other analysis that capture long-term data that allows you to determine how successful your process is going to be. But really, the fact of the matter is, I'm not sure that there's anything at this point, and we can take a look at more data at some point in time, that is really capable of predicting what a process is going to do, especially as well as they think the capability indices are doing. For a useful CPK, does at least partially depend on how you set your spec, LSL and USL? Well, if you're talking about process specification, yes. The more process specification you allow yourself, the easier it is to be able to meet it. But again, it has to be accurate to be useful. If you are running a process specification that is too tight, just because you're nervous about running it any further and you don't have data to support it, then you're going to be making adjustments more often than you need to. So the real key there is that you have to have a real tolerance to work within. That's how you get, probably your best analysis using a CPK. How can big data help us in SPC? I'm not sure that SPC is, I haven't looked at that. I'm not sure if SPC is a tool that is as effective with big data, simply because it tends to be very linear. It tends to be something that's looking at a very specific process. When you start looking at data coming from different directions and trying to deal with them as an amalgam, I don't think SPC is really a tool for that. It has a hard enough time with the total variance equation of the tolerances and what people believe to be a homogeneous process. So you can imagine, if you're trying to look at more facets of that data, how those tools really aren't very beneficial for that. Any other questions?
Well, I'm looking in the chat box and I'm not seeing any other questions, Bob. We'll give folks another moment or so if they have a question that maybe they're in the middle of typing in. Just want to remind everybody who's still online here with us that Bob will have his case studies that he's showing there on the screen on Tuesday, November 7th from noon until 1 p.m. Eastern time. So that'll be a bonus session for folks who are on today. If they want to come back and be online for the case study coverage, please do so. Looks like you're getting more questions, Bob.
There's a question about how do you set tolerance? Worst case scenario, Monte Carlo, root, sum squared. There's a variety of techniques out there for setting tolerance. Bookending is probably, the easiest and the most reliable, but I'm not really we're not really tackling that particular topic right now, but I would have to say the key though is that you need to have a very reliable tolerance mechanism, a tool that makes you confident that you have the correct tolerances before you can even apply capability to it, or you can be wasting your time. Here's one of my favorite ones. Will machine learning do anything for SPC for CNCs? One of the things that we have in CNCs is automatic tool adjustment. And there's a real problem when you use automatic tool adjustment because it's constantly adjusting. It's actually an algorithm of over control. It's constantly adjusting it back to a center target. And when you do that, you lose a lot of valuable information of what's occurring over time, especially with your tool wear. And if you're doing an OD or ID, for example, your roundness, or if you're doing a length, your parallelism. And what happens when you lose that data is you also lose the ability to understand what is actually going on with the machine and what's going on with that tool. And in fact, when I do capability studies with machines that have automatic tool adjustment, we turn it off, because it's the only way that you can actually see what that tool, what that process and that material is doing. So generally we try to avoid that, because you lose a lot of information with that constant adjustment. And it's interesting though, because it is an algorithm for over adjustment, which they tell you you're supposed to avoid. So it's quite a paradox.
Any other questions for Bob?
All right, if you think of any questions later on, please feel free to email me. I might be able to go over them during the next presentation. We really appreciate that too.
Okay, thank you, Bob. Looks like there's no further questions. As a reminder, next webinar that we will have will be on Thursday, November 2nd. That will be giving and receiving feedback with Sherry Bender. Hope everybody tunes in for that one. And as we mentioned before, Bob will be offering part 2 of today's talk, the case studies related to capability indices, on Tuesday, November 7th, noon to 1 p.m. Eastern time. So hopefully most of you will be able to make it for that. Until that time, we'd like to thank Bob once again for presenting today, and we'd also like to thank you all for turning out for this today. We look forward to seeing you at a future event, and until then, I'd like to wish everybody a good rest of the day. Thank you. Bye now.